Okay, and so we're going to use that as our measuring stick. What is that? We can think of that as one radius length, and that's one radius length no matter how big or small the circle is. That circle could be the circle that an ant is walking in, 2 millimeters. And then that distance right there would still be one radius length. That circle could be the orbit of a planet around the sun. Okay? That distance right there, that purple distance, is still what? 1 radius length, no matter what size the circle there is. Okay? So trig is all about measuring distances using the radius to do it. Things they never told you, right? Things they never told you. So watch. The first thing I'm going to do is I'm going to take that and I'm going to peel it off its normal place. I'm going to wrap it on the circle. Watch it again because it's just really cool. All right, there's the radius, how you're used to seeing it, kind of, almost, maybe. And then I'm going to take it and I'm going to pull it off its normal place and I'm going to wrap it on the circle. It still has a length of 1 radius length, okay? And I can continue to, starting from the positive x-axis there, I can continue to lay radius lengths on the circle, okay? So this represents, right there, that's starting here, 0. This represents 1 radius length here. And then, starting again from 0, I can lay another one, and so here is, what, 2 radius lengths. And then, almost halfway around the circle is 3, and let's just go to 4. And then that down there is 4. Okay, so what did I do? I took the radius length, and I'm starting to now lay it on the circle itself, maintaining its length. And so my distance from the x-axis then, in radius lengths around the circle, 1, 2, 3, 4. How many radius lengths to get exactly halfway around the circle? 6.28. Missing the boat. Missing the boat. How many radius lengths to get exactly halfway around? A little bit more than 3, right? Right. No, so exactly. So did you know that this is what pi means? Pi is 3.14159. Some of you memorized lots of places of this. Anybody memorize 50 places of this? I haven't. Okay, anyway. So this is what pi means. It's how many times you would need to take the radius and lay it on the circle to get exactly halfway around. Okay, so that's the first thing we're gonna do. The first thing we're gonna do is we're gonna take that radius length and we're gonna measure distance around the circle with the radius length, starting from the positive x-axis and going counterclockwise. And we get these different. We can mark off these distances: 1, 2, 3, 4. Halfway around is pi. All the way around is then 2 pi. Radius lengths. Okay, so then the next thing we're going to do is, let's go back and we'll show I need to aim for something else besides what I'm going for, and then I can get it. There. Got it. Okay. So, how many radius lengths is this? I fought hard for it. All right, so this is 1.2. So it's something past 1, and if you look down at the end slider, it's actually exactly 1.2. So I've got 1.2 radius lengths. 1.2 radius lengths from the positive x-axis along the circle, counterclockwise around the circle, okay? We're back. Here we go. So this was, what, 1.2 radius lengths of arc, right? And then we said that gives us a point, right? That gives us a point right here. And we wanted to talk about the x and y coordinate of that point, but we're going to still measure everything in radius lengths. And we said that the x coordinate was, what did I say, 0.36? And then we were just, that's where we left off. We were at the y. So what about the y coordinate measured in radius lengths? A half, 3, 7.5, -2. How many radius lengths would you say the y coordinate is? Almost 1, right? Maybe, yeah, 0.9 something, right? So let's say 0.95. It's almost a full radius length, but not quite, just a little bit shy. Okay, so I'm gonna give you a new arc length, and you're gonna repeat this. Take 1 minute to repeat it. Ready? Here we go. New arc length. Almost got it in the first try. Go. Go. So I want you to tell me what's the length of the arc, what's the x coordinate, and what's the y coordinate of the resulting point, all in radius lengths. Okay, what do we think? How many radius lengths of arc? Okay, so it's actually like 2.5, it's just 2.49, but it's 2.5. So 1, 2, and this is a half. This is about a half of 1 radius. So you should get something like 2.5. Yes, I started again. Thanks. Okay, what about x coordinate? X coordinate in radius lengths. 0.8. Negative, right? Negative. So we want to distinguish between going left and going right. We do that by just truly taking the x coordinate, negative 0.8 in this case, y coordinate. Yeah, about 0.6. Okay. So all these things are things you've heard of before. You just never conceptualized them this way. What is the first thing? What is radius length of arc the same as? Does anyone know? This is angle measure. This is how we measure angles. So that first angle, it had an arc length of 1.2 radius lengths. So it opened, it was an angle swept out of 1.2 radians. The second angle, 2.5 radius lengths, means it was 2.5 radians. So we can show it this way, the way you're used to here. So this angle right here is 2.5 radians because it's the angle that corresponds to an arc length of 2.5 radius lengths. So whatever the arc length is, that's how many radians of rotation or angle measure that you have. Okay, what's the blue one? Anybody know what the blue is? Measuring the x-coordinate using the radius length. You don't know what that is? This is the cosine. Now, cosine is a function that acts on the angle. The dependent variable of cosine is the angle measure, and then the independent variable of cosine is the angle measure, and then the dependent variable is the x-coordinate. So cosine takes an angle measure. That's why we did the angle measure first. And it returns to you, it's a function, it returns to you the corresponding x-coordinate. So what is the cosine of 1.2? Everybody. 0.36. What's the cosine of 2.5? It's a function. Its independent variable is this angle, and its dependent variable is x-coordinate, resulting x-coordinate on the circle. And then finally, the red one is the sine. Okay? So what's the sine? So the way we write it is sine of 2.5 equals approximately. Okay? Approximately 0.6. We were just eyeballing it. Okay? It's the same thing. It's another function. Its independent variable, or what it takes, is it takes angle measure. And then it returns for that angle measure the y-coordinate of the resulting point on the circle. Okay? So trig, everything, all the key elements of trig are all about measuring things on the circle with the radius. Okay? Whether it's angle measure, that's measuring arc length with the radius. If it's x-coordinate, you're measuring the x-coordinate with the radius, or if it's the y-coordinate, you're measuring the y-coordinate with the radius. And that's angle measure, cosine, and sine. Okay, another example here. Oh no, another yawner. 2 to deal with. You're okay. I forgive you. Okay, here we go. So estimate the angle measure, cosine of the angle measure, and sine of the angle measure. Estimate from the picture. Go. Over here. No, so the whole purple is 1. The whole purple is 1 radius length. And I'm interested in this point right here. I'm interested right here where that ray is, right? So this is the angle theta that we're interested in. Go, estimate those 3. All right, where's Kamal? F's here. Kamal here? How about Honor Middleton? Honor? Not here. Okay, how about Travis Geringer? You're up. Tell me what you said for the angle measure. Hold on, just the angle measure. So you said 0.85. Agree? Yeah. If you pick something close to that, that's good, right? So it's something shy of 1, something around, yeah. More than 4/5, less than 9/10, right? So more than 0.8, less than 0.9, so 0.85. This is good. All right, so now when we talk about the x-coordinate, we're really talking about now cosine of 0.85. So estimate cosine of 0.85. Where is Joel Reynoso? Tell me, what'd you say for cosine of 0.85? Yeah, good. So yeah, somewhere between 0.6 and 0.7. So yeah, I like 0.6. Your first thing, 0.68. That's good. Okay, sine. Jocelyn Robles. Jocelyn, tell me, what'd you say for sine? 0.75. Excellent. Yep, about 0.75. And what are those numbers, 0.68 and 0.75 again? What do they mean? What's the unit of that? Is she taking notes? What are the units of that, the 0.75? Not radians. Radians is angle measure that we get from the arc length. We get, so it's not 0.68 and 0.75 are not going to be radians, because that's angle measure that we get from arc length. Radius lengths, right? So it's 0.68 of a radius, about 2/3 of a radius, or 3/4 of a radius. Okay, so if this particular circle had a radius of 42 feet, then how many feet is that? So now we can think about the x-coordinate in radius lengths, 0.68, which would be true for any circle, right? But now if we have a particular circle that has a radius of 42 feet, then how many feet is it across? And then how many feet is it up to that point? Go, find it. How many feet across and how many feet up? Zach, you're up. That first one. 28.5. I'm interested in process, not answers. Oh, sorry. That's right. So you take the radius length, 0.68, multiply it by the 42 feet. Right. Yeah, so we want 0.68 of 42, right? We want 0.68 of 42. And so you got 28.6 feet. And so what did he do? He took the 42 times what? That's 0.68, which is the cosine of 0.85 to get the 28.6. All right, likewise, for the other one, you should have taken 42 times what? The 0.75, right? If you take 42 times 0.75, or 3/4 of 42, you'll get how many feet you are up. Should make sense. And so what is that really doing? You're taking 42 times sine of 0.85
That equals 31.5 feet now.
So for all circles, the cosine and sine for this angle will be the same. They'll be the 0.68 and 0.75, which is what? Fraction of the radius, no matter what the radius is. But if you're given a particular radius, say 42 feet, then you can nail down now your coordinates in feet, like we just did.
Okay, so this right here forms a triangle, right? This forms a triangle. And here's our angle. This is it's a right triangle, so the side opposite 90, the longest side is called? Hypotenuse. What's the length of the hypotenuse in feet? What's the length of the hypotenuse in feet? It's a radius, right? Isn't the hypotenuse a radius? So its length is 42. Okay? So if I come over here, this 42 is really what? Hypotenuse. And this is our cosine, right? This is our coordinate in measuring the radius. And then what is 28.6? So now that's the side, the x-coordinate is the side that's next to this angle, right? There's two legs. There's the blue leg and the red leg. The red leg is opposite, and the blue leg is, we call it adjacent, because it actually forms one of the legs of the angle.
Okay, so this definition, cosine being the x-coordinate measured in the radius length,
is where this comes from then. What is cosine? So then we can simplify that, and we get cosine equals what? The adjacent side divided by the radius or the hypotenuse. Same thing. So yeah, so the fraction that 28.6 is of 42
is how many radius lengths to the right we are, right? And that's why it's the cosine.
So if you took the fraction of 28.6 divided by 42, you'd get how many radius lengths you are to the right, or the cosine. And so that's adjacent over hypotenuse. Likewise, still the hypotenuse. This is the sine. This is the leg, that's the red leg here, is directly opposite of the angle. So we call it opposite, and that makes sine what? Sine equals opposite divided by hypotenuse. So I'm just going to divide both sides by hypotenuse.
Okay, but these two equations are not the punchline. The punchline is that what is cosine? Cosine is measuring x-coordinate in terms of the radius. That's where it all came from, and that's still the main definition for cosine. And then the definition of sine is measuring the y-coordinate using the radius. It's going to be whatever fraction of the radius you are, up or down.
As a result of that, those meanings, we get these equations.
Okay? As a result of those meanings. So that's the most important thing is measuring arc length, angle measure, measuring x-coordinate, y-coordinate, using the radius.
That's the big takeaway here. These equations are just results of that, right? So these are just consequences. Sine is opposite of hypotenuse.
That's not its definition. It's just a consequence of the fact that sine is the y-coordinate measured in the length of the radius.
Likewise, cosine. It's just a consequence of the fact that cosine is measuring the x-coordinate in the length of the radius. Okay? Any questions on the Trig crash course? You took good notes, right? Some. Others just watch the movie. Okay. Help you remember. So let's do this. Okay, so here's an optimization problem. And so we've got a pond as part of a outdoor race. They come to this pond with a radius is 1.8 kilometers. And they're coming in this way. As part of the race. So they come in here and they get to this point right here, and they got to make it to this point to continue the race. Okay, so they're going to come in at this point, and they're going to leave at this point, and they need to get from that start to that destination as fast as they can for this part of the race. So one of the competitors, Josie, she can run 4 kilometers per hour along the edge. It's a rocky, kind of uneven edge, it's hard to run on. So she can make it about 4 kilometers per hour, and she can swim 3 kilometers per hour. So she's got choices here. So when she comes here, she could just swim the whole way. So this is a situation where she just swims the whole way. Or she could run a little bit, get a little bit maybe closer, do less, and then swim from there, which would be less swimming. So she ran and then less swimming. Or she could mostly run and then dive in at the end and swim to the. Right. So what we see is lots of possibilities here. Lots of possibilities, and that's the idea of the variable situation. We've got things that are changing, quantities that are changing according to Josie's choice. Her choice as how to get from point P to the other side. Okay? Yeah.
It says they must make it by swimming and or running. So does that mean that Josie could simply run the whole way?
Yeah. So yes, exactly. So I just didn't show that particular that situation. If she wants to run all the way around, she can. Or if she wants to swim straight across, she can. Those are both valid. So how should she choose? Should she swim the whole way? Should she do some running and some swimming? And if so, what point P is going to give her, going to be the best? And so here's where we come to the last question of determining what best means. So how should she choose the point P to complete this part of the race as quickly as possible? She wants to complete this part of the race as quickly as possible. Okay, and what did we say last time? All these optimization problems, they're all about one particular thing. They're all about one thing. Let's see if we remember. Where's Jacob Osicki? Not here. How about Andre Diaz? How about Christina Smith? Christina, 2 days in a row. So these optimization problems, there really boils down to one particular thing. Do you remember what that is? Not sure? Jason Fox. Jason here, yeah. Do you remember what these optimization problems boil down to? What's that? That's a part of it. That's a very specific part of it. But the whole solution is about one particular thing. Alexis. Of what? Okay, it's still more detailed than what I'm talking about. Derek. No. Yes, sir. Okay. The quantity that is what? The dependent variable of what? Function. It's all about a function. Optimization problems are all about a function. A function, a function. They're all about a function. And what about that function? A function whose what? Dependent variable is a quantity What? Which quantity is it? What quantity is the dependent variable? Just in general. What's that? Yeah, the one that we want to optimize. The dependent variable is the quantity we want to maximize or minimize. So that's the first question we ask. What quantity in this situation do we want to optimize? Do we want to maximize or minimize? And then the whole solution is going to be about the function whose dependent variable is that quantity. So in this problem, what is the quantity that we want to maximize or minimize? I know Ian knows. Yes, sir?
Time to get across the lake.
And do you want to maximize that or minimize it? He wants to minimize time. Yes? Agree? That's it, right? If you want to get across the lake, the pond as quickly as possible, you want to minimize time. Therefore, we're going to build a what kind of function are we going to make then? Time function, right? Time function. There's dependent variable is time. Okay, so the question is, time is a function of what? Okay, time is a function of what? So we've got this, all these different possibilities. What quantity is going to pinpoint a particular possibility of all these situations where she could either swim the whole way or run a little bit or run a lot or run the whole way? So what quantity do we want to use here? Any suggestions for the quantity which will be the independent variable, right? The independent variable that will determine time. Okay, how far you run. Good, and so that should ring some bells. How far you run is really what? Which is? Radius length around a circle is? Those who took notes, radius length around a circle is? Angle measure, right? Angle measure. So this distance right here, if we measure that in radius lengths, that's angle measure, right? That's the angle measure from the swept from the x-axis, the positive x-axis. So we do time as a function of theta. Okay? Let's start with the applicable domain. What are all possible values of theta that make sense? What are all possible values of theta that make sense? So you think of what's the lowest to the greatest. Yes, sir. Okay, so 0 means what situation? 0 theta means what situation? Swims the whole way. That's 0 theta right there. And what's the greatest value of theta that makes sense? Right, so the full angle, it's not really in the right place, but this angle right here, if she runs the whole way, then we're talking about what we said, exactly halfway around the circle, which is an angle measure of pi. So our applicable domain is going to be from 0 to pi. All right, so now we need, we'll just do a generic, so some generic situation here. Okay, so we got to build this function. What's the time it's going to take her? So now this is just a generic situation where she does some running up to point P, she does some swimming. So what's going to be the overall structure of this function that's going to give us the time it takes her to do this amount of running and swimming? What will be just the overall structure of this function? Yes, her addition or sum. Is that what you're going to say also? Yeah. Sum of what? Go ahead. Be more specific. Sum of what?
The distance run multiplied by the speed ran.
And that will give you, you're thinking that's going to give you?
And then the distance swam.
And what are those products you're coming up with? What? So you're taking it a step further. I just want to know how sum of what? Sum of. Right. So yeah. So the time spent running plus the time spent swimming.
So let's break it down here. We're going to break it down into the time spent running and the time spent swimming.
Okay, and so he's offering up the time was distance times speed. Is that right? Distance times speed? That's what I heard you say. Is that right? So look over here. Is that right, guys? Yeah, what should it be? Yeah, so accumulation, so we can think of accumulation is like distance equals rate of change times a little change, right? Rate of change times a little bit of change is our little bit of change of time. So that means the time is distance divided by speed. So the distance running divided by speed running plus the distance, what, swimming, over the speed swimming.
So that's going to give us the time running plus the time swimming. Distance running over, or distance over speed.
Let's do V for velocity.
Okay, so what's the distance that
She runs. What's the distance that she runs? That comes from our Trig crash course.
how would I get the distance that she runs?
Okay, so the in radius lengths, how many radius lengths is it? It's going to be theta radius lengths, right? Because that's the definition of theta is the number of radius lengths. But we want it in meters, right? Or kilometers. So if it's theta, right? Theta radius lengths, and we want it in kilometers, and each radius length is 1 kilometer, then we want 1.8 theta. Okay, what's the speed at which she runs? That's given, right? That's the 4. So we got time spent running in terms of theta, right? We got time spent running in terms of theta. Angle measure or number of radius lengths times the length of each radius is going to give number of kilometers. Divided by 4 kilometers per hour will give number of hours to complete that part of that part. Then plus, we got the distance swimming over. What's her speed swimming? Velocity swimming? All right, 3. So this then is, we got to figure out what is this distance right here.
How are we going to do that? We got to get that distance that she swims from point P to the destination on the left. No, you're thinking about more arc length, right? Now it's a straight line, right? Straight line.
So that I think you were thinking about this. All right, so
how are we going to get that length right there? We just got to see it correctly.
Let me help you. Did anybody see that triangle?
That's the triangle you need to see. Okay? That's the triangle you need to see.
What is the height right here? This right here. Trig crash course. What is this right here?
Sine theta is in radius lengths, but we want kilometers, so
1.8. That's 1.8 sine theta. Now what about this? So is it 1.8 cosine theta? This much of it is, right? This much of it is 1.8 cosine theta from the center. Plus another 1.8. Okay?
And then how are we going to get that distance that she's going to swim?
Pythagorean theorem, right? It's your favorite math formula. Pythagorean theorem. So that distance she swam is going to be the square root of the sum of the squares of these legs. So I'll just write it down right here. So it's going to be the square root of 1.8 sine theta squared plus 1.8, right? 1.8 plus 1.8 cosine theta, all that squared. And all that under the square root. So that big square root is the length of that hypotenuse. It's the distance that she's going to swim. And that's all going to be over 3. And look, we got it. We got the function. We got the time as a function of theta. Function with its applicable domain. That's kind of the first half. The second half is now figuring out what theta is going to give me the fastest time. What theta is going to give me the fastest time? How much should she run around the circle to minimize her time? How do we do that? Just in general, how do we do that? So we want to find the minimum of this function within the applicable domain. How do we do it? What's that? Okay, to do what? What's the derivative going to help us with? Critical points, right? We're going to find critical points by taking the derivative and setting it equal to 0 and figuring out so whatever critical points we get, we'll figure out those times, right? The critical points inside the domain. And then also endpoints, right? Endpoints 0 and pi. So that's just we're not going to do that. I actually have a video where I finished solving this problem. I'll post that. You can watch the video if you're interested in how the rest of it goes. It's not short, because that function is complicated, right? Taking the derivative of that is going to take a little work, but it's not anything beyond what you can understand. It just takes time. Okay. So we're gonna find the minimum of this by considering all the critical points inside the applicable domain and testing the endpoints. And whatever time we get that's the least out of all those will be, or whatever theta we get, right? These are all values of theta. So whatever theta we get that gives us the least amount of time is the theta that's going to determine how she runs this, how she finishes the race, or how she does this part of the race to minimize her time. Any questions on that? So you have, for Thursday night, that third number 3 web work, you've got some required for homework. So out of the first 9, you have to do 3. And then out of 11, 12, 10, 11, and 12, which are all trig problems, you have to do 1. So I wanted to give you some experience with trig. It may be on the third exam, it may be on the final. So you have to have some experience with trig. Okay? And that number 3 web work, they're all due Thursday night at midnight. So 1 and 2 are extra credit. You're required to do those 4 problems in number 3, and then any more that you do in number 3 is extra credit. And in fact, in number 3, additional problems are with double, because those are longer problems. So any additional problems you do on set 3 beyond the 4 that are required, you get double extra credit for those. Okay. The first 3 sets are due Thursday night, and then then some more sets will open after that for the following week. Okay. Questions on that? Okay, and there won't be any other homework. I'll just give you the next 3 nights. You have the chance just to work on the web work. Okay, just the web work. Questions about that? Okay, we're gonna move on to the next topic. But so just if there's one thing you get out of optimization, they're all different, right? They're all these different contexts.
trig and distance and ladders and all these different things that you can come across. But the one thing that's the same about all of them is this process of building the function whose dependent variable is the thing you're trying to maximize or minimize, and then using that function, right? So that whole solution will always revolve around that key function whose dependent variable is the quantity that you're trying to maximize or minimize. That's your grounding on these problems, that they'll all be like that. So memorize that and keep that, as that's the path you're walking whenever you're solving one of these optimization problems. Okay. Okay, so if you were to put this equation, so new topic here, new topic. If you were to put this equation into graphing calculator, it would show you this. Why? So this is x squared plus y cubed minus 2xy equals 7. Okay? So is this equation just kind of like the name of this curve? Is that all it is? It's just kind of the name of that curve? Why does it show you that curve when you put in that equation? What do you think? Talk to the person next to you. Go. Why does it show you that curve when you put in that equation? Go. Okay, so here's a hint. This is two representations of the same thing. This is two representations of the same thing. What thing? Go, talk. This is two representations of what? That's the same. Go. Keep talking. All right, where's Julie Mays? Julie, what'd you talk about? Okay. Okay, but so how is this equation and this curve two representations of the same thing? Of what thing are they a representation of? Yeah. Okay, so all possible what? Right. So it's what? It's values of x and y taken together that either make that true or what are points on that curve. So they both are representing what? The same set of points. Okay? The equation and the graph are mathematically the same because they both represent a set of ordered pairs. How does that set of ordered pairs relate to the equation? How does that set of ordered pairs relate to the equation? Makes it true, right? So what can you say about this point right here? If you took its x and its y and you plugged it in here, it would be 7. Red. What if you took this x, say x1 and y1, and put it into this expression? Something other than 7. It wouldn't be 7. If it were 7, then it would be a point on that curve, right? If you take those two x coordinates and put it in there, and you don't get 7, then you're not on the curve. If you do get 7, you're on the curve. So they're both representing a set of points. The set of points make the equation true, and are all the points on that curve. Does the set of ordered pairs represent y as a function of x?
For a given x, do you only get just one y? Always. No, there's lots, you can see lots of x's there, around 2, 3, 4. Where you're getting more than one y, so it's not, no. Okay, what about the rate of change of y with respect to x? Is it valid to talk about the rate of change of y with respect to x, or a rate function? Is that valid? Okay, so for x equals 3, is there a particular rate of change? There's 3 of them, right? But now what if I said this point? If I just said, I care about the rate of change at that point. Can you tell me? Or could we figure it out? Yeah. So we can have a rate function. It just can't be a rate function as a function of x, right? What could it be a function of? Could it be a function of y? X and y. It could be a function of an ordered pair that you pick, right? So we can have a rate function as long as it's a function of points, x's and y's taken together. Okay? But we can't have a rate function as a function of x because there's more than one rate for a given x, and we can't have it just be as a function of y, but as a function of ordered pairs, that works. All right? So it's valid to talk about rate of change. And yes, we can have a rate function if the independent variable, quote unquote variable, is an ordered pair, not just an x value, right? Okay, so, but in order to determine dy dx, it's kind of like we kind of have to suppose that y is a function of x. Okay, we know that it's not, but it's kind of like we have to pretend that it is, all right? And so in other words, y equals f of x is implied, but it doesn't necessarily exist. Like in this case, it doesn't exist. Y is not a function of x. But to talk about developing a rate function for this, we're just gonna say that y equals f of x is implied. Okay? And then, so in order to get that rate function is what we call implicit differentiation. We have to imagine that there is this function y equals f of x. It's implied, but it's not really real, okay? And that's, in order to get the rate function, that's why we call it implicit differentiation in order to do that. Okay, so here's how it works. I've got this equation, okay? And rather than it being y as a function of x, we're just going to imagine that y is a function of x, right? So the fact that y is a function of x is implied, although it's not really right. It's not really real, okay? But we're just going to suppose that it is. So anywhere there's a y, we have this imaginary function of x, okay? And now we're going to take the derivative with respect to x. So I'm going to differentiate the left side with respect to x, and I'm going to differentiate the right side with respect to x. Okay, and so again, now we're going to follow all the same rules that we learned for the mastery test. On that left side, we're going to look at the overall structure of that thing. We're taking the derivative of something. What's its structure? That's going to govern or determine how we approach it. So on the left, what are we going to do to take the derivative of this thing? What is its structure? X squared plus y cubed minus 2xy. What is that? Sum and difference. That's our easiest rule, right? All we got to do is do the derivative of each individual one, right? So we start with the first one. Derivative of x squared is 2x. Okay? Now we got the derivative of a function of x cubed. How do we do the derivative of some function cubed? We're going to need the chain rule. That's a composite function, right? That's one function plugged into another. So applying the chain rule to that. So the derivative of x squared we said was 2x. All right, so now we got to apply the chain rule. And we're all masters. Most of us are masters. Some are still
Catching up. Okay? Chain rule would say
3 times f of x to the second power squared. And that's it, right? Chain rule tells us we also need times derivative of the interior, right? Derivative of the interior, f prime of x. Okay, now we got minus 2x times f of x.
How do I take the derivative of that? What is it?
Structure. It's a product, right? It's not the derivative of the first times the derivative of the second, right? Anytime you come to a product
In calculus, and you're taking the derivative, it will always be the product rule. So here we go.
it's going to be, so we'll do minus 2x times f of x. So derivative of the first times the second plus the first times the derivative of the second. So that's the whole left-hand side.
I got 2x, derivative of x squared, then I had chain rule, then product rule. What's that?
No, because everything's, multiplication comes first, and then addition. So I'm not multiplying by any sum here. That would be if I was multiplying by a sum, then I'd need parentheses. All right, so that's the whole left side. And then the right side would give us derivative of 7. 0.
And what was I after in doing this? What did I want to find?
I wanted a rate function, right? I wanted a rate function, dy dx. Where do I see that in what I just did? Where is that? Where is dy dx in here?
dy dx is?
Just another name for f prime, right? F prime is dy dx.
So I want to solve for that. If I want a rate function, then I want to know what dy dx is. I want to know what the derivative is. So that's another name for that's f prime, so I'm going to solve for that. So I've got 4 terms there. All the terms that have an f prime, I want to have those on the left. Keep those on the left, or move them to the left. Any term that doesn't have an f prime, we're going to move that to the right side of the equals. Okay?
So this is going to go, right? This is going to go right. This is going to stay. This is going to go right. And this is going to stay. So my blue ones are going to stay on the left because they have an f prime. And the reds are going to move to the right because they don't have an f prime. So I'm going to have 3 f of x quantity squared times f prime of x minus 2x f prime of x equals negative 2x plus 2 f of x. And then I'm going to, this is times, I'm trying to solve for f prime. So now that I have all f primes on the left, I can factor it out. Last step, solve for f. How do I solve for f prime? Just divide by everything in the brackets there, right? So f prime is going to equal negative 2x plus 2 f of x all over minus. Okay. And what was f of x again? Where did the f of x come from in the first place? That was just y, right? We were saying y is some implied function of x. And we used that to help us see that it was chain rule. But really, f of x is just y. So I'm going to replace those with y. And we got it. So we've got dy dx. And look, lo and behold, it's a function not of x and not of y, but of ordered pairs, right? So you need an x and a y. And then given an x and a y on that curve, this formula will give you the value of the rate of change of y with respect to x. So let's just let's leave it at that. Okay, so in solving these problems, you don't have to change it to f of x. You can leave it as y, but you have to remember that it is a function of x, and that anytime you differentiate and it has a y in it, that's going to require the chain rule because it's implied that it's a function of x. So the reason we want to do it that first time is to really see we need a chain rule, right? Every time we take the derivative of y, so you can use y's and y primes. You don't have to use f of x and f of x primes. It's a little bit less writing, okay? But really important to see what's going on there. I think the f of x is really helpful the first time. Okay, any questions on that? So let's take a look at this. So what was the equation? Okay, and then we got our rate function was? So I'll call it d of x. So it's a function now of two variables. Tell me again. Okay, so let's just pick a point here. This one I talked about, right? Okay, that's pretty much 3. So the point is 3, 2.26. What would you estimate the rate of change is going to be there at 3, 2.26? You don't have to give a number, maybe just qualify, right? So we know rate of change is about how fast y is changing with respect to x. So is it increasing, decreasing, slowly, moderately, or rapidly? Remember, that's what the rate of change gives us. So what would you say? Increasing or decreasing, slowly, moderately, or rapidly? Decreasing slowly. So what should the value of the derivative be? Small negative. So if I come here and I go d of, capital D of, what? 3, comma, 2.26. Is it agree with our estimate? Negative 0.16. That's like negative 1/6, basically. Does that reveal, or does that reflect that at that point, y is decreasing slowly compared to x? Yep. So this implicit differentiation gives us the rate function for curves, but it has to be a function of x and y ordered pairs, right? It can't be just a function of x or a function of y, because we don't have a function of y as a function of x. So we need rate function in x and y. Okay, web work for Thursday night. Work on your web work.